Hey everyone, welcome to Code Harmony. Today we are going to solve LeetCode from ID 1504. Count some matrices with all ones. This problem is a very interesting problem asked in Google several times. In this problem, we'll be using or utilizing concepts based on arrays and monotonic stack. First of all, our aim will only be to solve this problem, and then later on we'll see how we can optimize it further. Because it is marked as medium, but it might be a bit challenging for the beginners. So let's have a look on the problem statement first. We are given m cross n binary matrix mat. Now return the number of submatrices that have all ones. Number of submatrices that have all ones. They are saying number of submatrices. They are not saying number of square submatrices. So any submatrix can also be of size any number of size, m cross n, a cross b, anything. And the given is that the size of the given matrix is m cross n. So from this m cross n matrix, I need to count all the submatrices where all the elements are 1. So this is something we have to do, and we have to return the number, that integer we have to return. And what are the constraints? M and n will go till 1000, and it is a binary matrix. So if we try to count the numbers, let's count the number manually. This is one matrix. This is one submatrix, 2. This is another one, and this is another one. This is another one. This is one. Now, how many so far? 1, 2, 3, 4, 5, 6. 6 we have calculated. 1, 2, 3, 4, 5, 6. Okay. 6 we have calculated so far. And now let's see what are the total numbers of matrices. If I try to end with this, it can be the whole one, below 2, and this third one, 3. 3 more matrices I have calculated. After that, time for this matrix. This one, 1, 2, 3, 4 plus 4, which is 13 in number. 13 matrices. It means 13 matrices I can form using this small matrix. So if it is given something like this, 1, 0, 1, 1, 1, 0, 1, 1, 0, from this matrix, any submatrix where all the elements are 1, those matrices are 13 in number. It's a big number. So definitely, there are a lot of challenges while calculating this number. So this is something we have to do. I hope the problem statement is clear to you, and now we will see how we can solve it. Let's try to build our approach. Here in this matrix, we'll have to find out a submatrix where all the elements are 1. And now to do it every time for every submatrix, grid within this grid, that has become more challenging, more confusing. There are so many calculations and so many iterations over the column wise and row wise. So what I will do is I will try to make it a bit short, or maybe try to extract out some sub problems out of it. And let's see that we are trying to find every single submatrix where all the items are 1, ending at a specific index. Let's say this index is I, j, and let's say that is this index. If this is the position I and j, I will try to find out all the submatrices, valid submatrices ending at this position. And those submatrices are this one and this one. That's all. Okay. Let's take one more example. How do I find out all the submatrices ending at this position? This one, and this one, and the whole. If I try to zoom it out, let's say initially I was at this position, 1, 1, 0. So there was something like this, one matrix, there is only 1, 1. Second matrix is this. The second one was 1 1 0 and 1 1 0. This was the one, and the second one, and the third one, and the fourth one. Okay, fourth one. So what I'm trying to do is I'm trying to fix some coordinate so that I can easily find out the bigger problem, solution to the bigger problem. So if we have to look for the sub problem, it can be something like this. Find all the submatrices, valid submatrices ending in a specific position, I and j. So now in this case, this is fine, but here this situation is having a lot of confusion again against multiple rows. We are going up as well. We are going on the left side as well as the up side. Instead, if I am writing it something like this, the third row, if I am writing it something like this, if I try to convert it into a form of histogram, the first position can go till 3. The second position can go till 2. Third position is already 0. And now I wanted to find out all the submatrices ending at this block. All the submatrices ending at this block. If it is a histogram, let's capture the height. It is of 3 height, it is of 2 height, it is of 0 height. So here in this histogram, if my second bar is going till 2, I can see what is the height. What is the height of what are the different submatrices I can form ending at this block, this highlighted block, this one and this one, right? But previously blocks we should also be captured. So previously we should capture something like this ending at this position. This red block should always be there. If this red block is mandatory to capture, this can be one rectangle, right? One rectangle, two rectangle, this 3 rectangle itself it is, and the fourth rectangle is the fourth one, right? So what I'm trying to explain is that instead of keeping the whole matrix together, if instead of taking the whole matrix, why not we just take this complete row, independent row, making rows independent. If I have this row independent, I can also get the answer. If I have the matrix, I can get that, okay, ending at this position, I can only have 4 rectangles. But if the row is independent, and the row is something like this, 3, 2, 0, this is something like a histogram, the bar chart, 3, 2, and 0. I can still find out the answer. How many rectangles are there ending at this position, ending at this position, ending at this position. We are finding all the rectangles ending at I and j. I is already fixed, j we can fix while moving in this direction, right? So the conclusion here is make rows independent. Try to make all the rows independent. Let's see how we can make it independent. 101, 110, 110. Okay, so this matrix is given to me, and if I try to make every single row independent, so it will be something like this: 101, 2, 1, 0, 3, 2, 0. So this is like every row is now independent, and what I can do, I can process every row individually. So the same logic I can apply for this row, same logic I can apply from this row, and same logic I can apply to this row as well. And why I did this? Because I don't have to carry the whole rectangle now, whole the grid now. So first row is independent, second row is independent, third row is independent. Okay, now what I have to do is I have to write some magical function which is going to give me the count rectangles in a specific row, and that is going to be my answer. My answer plus is equal to count rows in every single rectangle. For now, just for the sake of understanding this problem statement, just assume that, let's say I have already implemented this function, and now your responsibility is to make every single row independent. Firstly, how do I make every single row independent? First row is as it is. Second row, let me write it completely. First row as it is. Second row, if it is 1, just include whatever is the value on the upper side. If it is 1, it is 1 plus 1, that is 2. If it is 1, 0 plus 1, which is 1. If it is 0, 0 means 0. The tower is broken. 0 means 0. So for this portion, 1 plus above it, it is 2. 2 plus 1, 3. 1 plus 1, that is 2. If it is 0, then it is already 0. So this is, I have made the every single row independent, and what I have to do is I have to pick this row and pass it to this function and get the answer. Later I have to pick this row, pass it to the function, get the answer. I have this row, pass it to the function and get the answer. I am iterating row wise from row 1 to row n minus 1, one by one, right? Why I am telling you this? Because we can still save some space if we are doing it simultaneously, synchronously, one after another. Then what is the need of pre-processing every single row? There is no need to make every single row independent in advance. Do it one by one. Try to make first row independent, move to the pass to the function, get the answer. Try to make another next row independent, pass to the function and get the answer. Okay, so for now we have two ways, but ultimately we have one work to do: make every single row independent. Okay, and now once I have made every single row independent, I just have to use my formula to get the answer. Let's say I pick the second row. What is the second row? 2 1 0. 2 1 0. Let me give you a recap. We are given a matrix, which is a binary matrix, and we have to find out every single rectangle where every single item is 1. What I did is, my step 1 is completed, that is making every single row independent so that I can process them comfortably. I just have to pass one array. So this is like row. Row is an array, and I'm going to pass it to my function, and that function is going to give me every single rectangle I can form with this array. And this problem I am relating it to one standard problem, very standard problem, that is maximum area of a histogram. Maximum area in a histogram, it's a bar chart given to us. In this bar chart there are so many rectangles I can form, so just whatever is the maximum area, just return that. That is a very standard problem. I am relating it to that problem. But if you still do not know that problem, that is not an issue. It is a 2 size block, then it is a 1 size block. The size of block is 0. My I is already fixed. I just have to fix my j. My j will start from 0 and j will go till n minus 1. Why n minus 1? Because the dimension was m cross n. So j is going to go from 0 to n minus 1. That is perfectly fine. So now at j equal to 0, I will try to find out every single rectangle which is valid. So at j equal to 0, the height is 2. Height is 2. Okay, that is fine. So what I can do is, at j equal to 0, I can have a height of 2, or maybe less than 2, or maybe 0 or 1 to anything between 0 to 2. Why I'm saying this? Because let's say that there is one tower of height 1. There we can include this portion as well. Correct? We can include this portion as well. So it means that ending at 2, the maximum height I can have is of 2 size. And that too with all the previous items. You will understand it once we try run over different kind of examples. So just stay with me, you will definitely understand it. Firstly, height is 2. My height is 2, and over the left side over the left side I can't go anywhere. I can't go anywhere on the left side, so we have a width of 1, height of 2, width of 1. So but in this case, whatever is the height is 2 here. I think 2 is going to be my answer, because I can also take 1 height block, I can also take 2 height block, I cannot take 0 height block. So whatever is the height value is 2. That is something I can take. So my, maybe let's say result plus equal to 2. Okay, when I come to j equal to 1, I'm at this position, second bar has a height of 1. So it is just 1, like not more, less than 1, not less than, greater than 1 we can go. So as it is 1, so what is the portion I can move on the left side? So height is 1, and at this 1, how many portion I can move to the left side? 1 portion from current j value, so 1 portion from the previously j value as well. So because previous value of j is 2, so I can include this block as well. So 1 into 2, 1 is height and 2 is width. So whatever is the value, I will just include it in my result. So plus 2 I will include, and at value j equal to 0, if the value is 0, then we can't form any rectangle. So it's done. So this row is done, and we will be able to find out or figure out 4 rectangles. 4 rectangles where the base is second row. Okay, so what are those 4 rectangles? Let me also show you. 4 rectangles where base is second row. 1, 2, 3 and 4. Okay, that is perfect. That's perfect. So we are going to use the same logic. So let's try to do it for the whole row. First row is 1 0 1 1 0 1, ending at this block. How many rectangles I can form? 1. Ending at this block I can form 0. Ending at this block I can form only 1. So that is 2. 2 from first row and 4 from second row, and what from the third row? 3 2 0. 3 2 0. Starting with j equal to 0, I can form 3 rectangles. Height 1, height 2, height 3. I can form 3 rectangles, and starting at j equal to 1, j equal to 0, j equal to 1, j equal to 2. When I'm at j equal to 1, I have 2 heights. For 2 height, I can make like 2 width rectangle. For 1 height, I can also make 1 width rectangle, 2 width rectangle, correct? So whatever is the current height, my current height is 2, and with the current height I can make 2 rectangles. It means these 2 length rectangles we can form. Plus for 1 height I can make 2 rectangles. For 0 height I don't consider, so that is 3 plus 4. Okay, for j equal to 0 we can't form anything, so it is like 3 plus 4 plus 0, that is 4 plus 3 7. So 7 rectangles I can form with this histogram. So 7 plus 4 plus 2, 7 and 10 11 and 2 13. So 13 is going to be my answer. So far what you have understood is, try to make every single row independent and then check for this formula. count rows. Now let me work the same example on a same approach on a bigger example. Let's pick this. What I will be doing is I will try to make every single row independent. First row is 0 1 1 0 0 1 1 0. If I try to draw it in the form of a bar chart, it is something like this: 0 1 1 0. Ending at this index, how many rectangles I can form? I can form 0 rectangles. Ending at this index, how many rectangles I can form? This rectangle has a height of 1. So I can either check for 1 height rectangles or nothing else. So 1 height rectangle is only 1. Ending at this position, how many rectangles I can form? Only one height rectangle. How many one height rectangle I can form? Yeah, here it is a good point. So this is one portion and this is another portion. So 1 height rectangles I can form is 2 in number plus 0. This is the code. So for second row, try to make the second row independent, and second row, to make it independent, it is something like this: 0 1. If it is 1, check for the previous one. 1 plus 1, that is 2. This one plus this one, that is 2. This one plus 0, that is 1. So 0 2 2 and 1. 0 2 2 1. Ending at this block, how many rectangles we can form? That is 0. Ending at this block, how many rectangles we can form? See, the height is 2. So we'll check for one size height. We'll check for two size height. So one size height is nothing. I cannot go on the left side. This is the only portion. So one size is 1 and two size is also 1. Now I'm coming here. Here, one size I can form 2. This one and this one. See, this one and this one. This one and the complete one. So 2 I can form. So one size I can form 2 and two size I can also form 2. So here at j equal to 3, one size I can form 3. This one and this one plus 3. So 0 plus 2 plus 4 plus 3 is the total number of rectangles I can form where the base is second row. 4 5 6 7 8 9 3 2 and plus 3 and so on. You will just keep on doing. So the main part of this question, I think, is that counting how many rectangles we can form. So for that, what I can do is I can use order of n square time to find out that value. We'll have the value of the second row. Second row, let's say that is 0 2 2 1. So 0 2 2 1. Let's try to build the pseudo code for this approach. First of all, we have to go to every single j. J is equal to 0, j less than n, j plus plus. Starting with every single value of j, I will do something. And then let me also create a bar chart here. That is 2 size, that is 2 size, that is 1 size. Indices are 0, 1, 2, 3. These are the value of j. Okay. For 2, ending at a specific j, what I need to find out? First of all, let's say that current height is the minimum height. Minimum height is value at j. Okay. Minimum height is 2. Then what I will do is, starting from here, I'll keep on going till 0. So for k is equal to j, k greater than equal to 0. I will keep on going here, or until the height has not become 0. Whatever is the minimum height. So at this position, minimum height was 2. So I added to the answer. So at this position, the height is 0. So I just have to stop here. If it was something like this 1, so capture the minimum height. So minimum height is equal to minimum of current height, like current value. Current value is at k. Okay, so that is the minimum height. And this minimum height is going to contribute to the answer. So result plus equal to minimum height. Let me highlight it. When I was at j equal to 1, so height is 2, so 2 got contributed to the answer. When I'm keep on going on the left side, because ending at current position, I need to check for all the answers. I'm coming here at j equal to k equal to 0. So here I see that the height is 1. If the height is 1 here, then 1 will be contributed. How? This is the portion ending at this position. See, this is kind of logic I will be using, and this is going to give me some time around order of n square to find out all the rectangles in this histogram. All the different rectangles in this histogram I will be able to find out in order of n square time, and to independent the rows, that is also order of n square time. Order of n square time to independent the row, and then after n square, how many rows we are having? M number of rows. One, 0, 1, 0, 1, 1, 0, 1, 1. First of all, we are making every single row independent. The area, the size is order of m into n. If I am making every single row independent, it is m into n. But instead of making every single row independent by one, I will make it independent and then pass to the function. Make it independent, pass to the function, make it independent, pass to the function. So how many rows we made independent? M number of rows. So for every row, we are applying order of n time to make it independent, and after that order of n square to find out number of valid rectangles in this row. So for every row, I am going n square. So overall time complexity is m into n square. This is the overall time complexity. And this was the complete approach. I will be attaching the code in the description below. And let's have a look on the code now. Here in the code, if we try to have a look, we have a dimension of m cross n. And this is the height array to temporarily store my current independent row. Current independent row. Because I am not creating the whole rows at one go. Do it one by one. So first row, let's try to, we have m number of rows, right? So first row I made independent, and then I have a height array, and height array I'm going to pass it to the count rectangles. And this function is something like, we are given a histogram. Let's say histogram is 2, 1, 0. In this histogram, how many rectangles are there? Number of rectangles in this histogram. And that is something I'm calculating, that ending at every single specific j, what is the size, how many rectangles I can form. So ending at j equal to 0, whatever is the rectangle I can form, I will add it to the answer. For j equal to 1, I will add it to the answer. So for j equal to 0, this is the code. Minimum height is, here the minimum height is 2. I will keep on moving in the left direction. Here the minimum height is 1. So 1 added to the answer. Keep going in the left direction. In the left, from the left side, we can also get a piece of 1. So minimum height, we can get a piece of 1. So here, if it was something like this 0, 1, 1, 0, from this portion, we'll get a piece of 0 height. So just do a dry run, couple of examples. Just try to make it over this, over both the examples. You'll be able to get more clarity. Okay, and yeah, this is the code. And here, this count rectangle is actually a brute force way of doing it, but it is going to be get submitted. 97% faster. Why? The constraints are not so high, but this portion, this count rectangles can also be done in order of n time. In order of n time using monotonic stack. What is this monotonic stack? Monotonic stack means keeping stack in a specific order, and this monotonic stack code I have also written here. What I will do is I will try to keep track of heights in the increasing order. If I am taking this example, in this example, what is the second row? Second row is 0, 1, 1, 1. After making this row independent, I got 0, 2, 2, 1. So 0, 2, 2, 1 is the row that I got. And now from this row, I want to count the rectangles. Count rectangles. So for that, to count rectangles, let me mark indices 0, 1, 2, 3. And this is my J pointer, J point for this loop. Along with this, I will be keeping a stack. I am keeping the stack, and this is something to keep this stack monotonic order. It means that stack should not be empty. If it is not empty, that's the only time we can remove something out of stack. Pop. So if whatever is the value at the stack, the value at that index in the array should be, if it is greater than h of I, just remove that. It means that is of no use. Right now this case has not arrived, but later on you will see. After that, if the stack is not empty, do something else. If it is empty, do something else. The stack is already empty. The stack is already empty. Then what I have to do is I have to do this. Sum of j. It means sum of all the rectangles ending at j, current j, is equal to whatever is the height of the current element. Height of the current element is 0 into whatever is the value of j plus 1. See, this formula is saying that if the stack is empty, it means that my current j, whatever is the height of my current j, it means every single item so far has at least that height. At least that height. Okay. It is something like this. Let's say 1, 1, 1, 2, 1. If I'm at this and my stack is empty, and I can confidently say that at least starting from index 0 to this index, all the element is having at least height 1. So this is the case. So this case is covered, right? And now after it is covered, stack may push karo j value. The value of j is 0. It got pushed to the stack, and the current value, some value, is got added to the answer. So answer is my 0. Answer is still 0. Okay, now the value of j is done. J will be pointing to the next item, that is 1. And at the next item, I will see, do I have to filter out items from the stack? I will filter out items from the stack if those items are already bigger than my current value. It means that is understood. So I have this one in the stack, I have this one in the stack, I have this one in the stack, and I have this one in the stack, and I am not having this one in the stack. It means that it is already understood that if any item between these two items are not in the stack, it means that that portion is having at least this much height. This might be a bit confusing, but it's a standard problem. This is for the one who are not the beginner to this problem and came here to get some value out of it. And those who are already beginner, you have to firstly submit the problem using the same approach we have used, and that approach is nothing, just iterations over the array. Okay, so j is 1, the value is 2. The value is 2. What I have to do now, stack is not empty. It means that stack is not empty. What does it mean? That whatever is the value at the top of the stack, index 0, after index 0 till my current index, which is 1, there are all the items which are of at least 2 height. So after index 0 and till index 1. So after index 0 means 0 exclusive. Till index 1 means 1 inclusive. All the items are having a height of 2. So after index 0, to bacha ek hi item. There is only one possibility, that is 1. So it means, what is the height? What is the height value? Height value is h of j. That is the height value. And what is the minimum height? And what is the number of items that are having the height of this one? See, stack is not empty. It is showing that till this 0 the height is lesser, but after this 0 till the current value of j, all the elements are having a height of equal to j. So all the items have height equal to j. It means height of j equal to j minus stack dot peak. Stack dot peak. What is this? Stack dot peak j minus stack dot peak. This portion. Okay, this portion is clear. And now along with this portion, there is one portion as well, sum of previous. So what is this sum of previous? Sum of previous means all the rectangles ending at index 0. All the rectangles ending at 0 index, they have height less than height of j. It means they can also be included in j. So let's say this is the previous one. This is the previous one and this is my j. It means all the items from here to here, they have enough height till j. Let's say j height is 1.1. So these two items have enough height than j. So height of j into j minus peak item, that is fine. But if there are items in the stack, it means they are also having some height. Okay, whatever is their height is expanding till this current j. So whatever is this range, just multiply it with this. Not multiply, we have already calculated that this is the latest value in stack. Whatever is the number of rectangles ending at this j, they can also be expanded to the current j. So they can also be expanded to the current j. That's why sum of previous we am using. So plus sum of previous. So these are the two formulas which is very important, and those two formulas are forming this equation. And this code is something like a concept, that area in histogram. And what we are doing is we are finding number of valid rectangles ending at every single position in histogram. Number of different rectangles I can form ending at every single j. So why this approach is beneficial over the previous one? In the previous one, we found out the number of rectangles in every single row in order of n square time. But here we will be able to do it in order of n time, but order of n space. Order of n time and order of n space. So overall, this stack approach is going to reduce the time complexity to order of n square than the previous one, which is order of n cube. Okay, so this is all about this problem. This section was on a slightly medium to hard side, but the previous one is a medium kind of thing. Let's see the code for this as well. We have already seen the code. The code is something like delete all the items, and here this portion is going to help us keep the stack monotonic. After that, this is something where we have to put our brain. Just common formulas we have to derive using examples and then capture it. So to practice this problem, do try to make a dry run over the examples and check out both of these approaches. I hope you have understood something out of this video. Thanks for watching, guys. Bye bye. In case you get any doubt, do let me know.